Okay, we've got about 5 minutes for everybody to log in there, so let's go ahead and get started. Today we have a warm-up where we have a quadrilateral inscribed within a circle. And when it comes to this quadrilateral, we have a little bit of information about it. We know that the measurement of angle ADC is 80 degrees. The length of segment BC is 36 units, whatever these units are. The measurement of length AC, that chord, has a length of 68 units. And what I want to know is, what is the measurement of angle BCA? If I was you, I would go ahead and I would start off by copying the diagram and labeling the numbers on there that I gave you so that it's easier to see what information we have to work the problem with. And then after you solve for the measurement of angle BCA, look at what other information is there, right? And we're going to go through and just talk about, without actually doing it, but what other things are therefore calculable based on these first 3 digits. The answer might surprise you. And just so that we're clear, guess why I would even include segment AC? Why would I give you a quadrilateral, but then also define one of the diagonals?
You want us to do some sort of triangular trigonometry.
Correct, yeah. This is actually a trigonometry question. That's typically the only reason why somebody would add a diagonal that helps you define some of the inside parameters of a polygon. And on top of that, is AC the diameter?
Nope. No, way far off of the central point.
Yeah, so how do you know that AC is definitely not a diameter? Like, it's not even about the way it's drawn. It is definite that it is not the diameter.
Because the triangles aren't congruent or something?
Not quite. Again, it has nothing to do with the way it's drawn, and it has everything to do with definitions and phrasing and rules. What is the name of the circle?
Circle P. So therefore,
what is the naming convention for circles? How do we call them?
So that means
based on their central.
It has to go through P in order to be diameter.
Right. If this is the name of the circle, then that means point P is necessarily the center of the circle. And if AC doesn't go through that center, it ain't a diameter. So like I said, draw your own version of the diagram, fill out the numbers that I gave you, and start working the problem. I think you'll find that after one trick that we've learned this chapter, then the rest is basic trick. In the meantime, though, let me go ahead and get the answer key up. I forgot to upload it last night. So I just scanned it, and I need to put it up. I'll put it up in a second so that y'all can take a look at it. And then we'll go over the quiz and such. Of course, today we have a new section of notes to go over as well, so it'll be kind of a busy day before we head off to lunch. Those scans are ugly. They're readable, but they're ugly. My bad. Okay. So let's go ahead and begin. So like I said, it's always best whenever you're given a problem to label the bits and pieces on there, just because I think it makes it easier to see what the necessary relations are that we're going to be taking advantage of. So inside of this circle, I have my quadrilateral, and I know that the measurement of angle ADC right here, well, that's 80 degrees. I know that the measurement of BC, that's right here, that's 36. AC, well, that's right here, that's 68. And what I want is I want the measurement of angle BCA, which is right here, not the whole angle, but just this piece of it right there, right? And so what I want to know is, what is that? How do we work this problem? What's the deal?
Well, we know that opposite angles in a quadrilateral that's in a circle are supplementary. Therefore, angle B is going to be 100 degrees.
Very good. And that is one piece of information that we need from the current chapter to work this. If this is a quadrilateral inscribed within a circle, opposite angles have to be supplementary. So if this is 80, necessarily on the opposite side over here, angle B, well, that has to be 100 degrees. And I'll just put that in a color to show that that's something that we reasoned out, not something that was given to us. And so, based on that information, how can I now work this triangle? And if you have a hard time seeing it, you know, just draw it out separately as another triangle. Yes?
Use the law of sines.
Good. We can use the law of sines because we have an opposite side and angle pair right here. So then that will let me solve for this angle, right? But is that what I want?
No, but you could use the third angle theorem.
Correct. So the law of sines will let us solve for measurement of angle BAC. That'll give us this. And once I have that angle along with the 100, then we can get the angle that we were asked in the first place. So that is to say that the setup that I'm going to be using here is going to be sine of 100, then divided by its opposite side length, which opposite of that 100-degree angle, we have our length of 68. And this is going to be equal to sine of angle BAC, then divided by 36, because that's its opposite side length. And so this setup right here will let me solve for the measurement of angle BAC. The reason why we do this is that, like I mentioned, that trig that I taught y'all, that's the most important thing you need to take away from this year. That's the thing you should leave still being able to do next year, because you will see trig in Algebra 2 in a big way, and you will see trig in an even bigger way in pre-cal. So how can I get the measurement of angle BAC alone? What algebra do I have to do to untie this knot?
Multiply.
Multiply both sides by
36. Oh, 36.
That'll give us 36 sine 100, then divided by 68. This is going to be equal to sine of angle BAC. And what undoes a sine? How do I get rid of this sign?
Inverse sine.
Inverse sine. So this is to say that inverse sine of 36 sine 100, then divided by 68, all of that together on the inside of the inverse sine, well, that will give me back the measurement of angle BAC. And then will be one simple step of arithmetic from the end. So that is to say that I'm going to do 36 sine 100, then divided by 68. And what do we have to be careful of when we do trig? What do we need to be aware about our calculator?
Degrees mode.
Got to make sure it's in degrees mode. So I'm going to go to mode. Okay, yep, we're good. Second quit. So I'm going to hit enter on that. So that gives me the decimal. That's just what's inside of here.
Yeah.
And now to get the angle measurement, I have to do second inverse sine of that number. And so it's 31.42 degrees.
Yeah.
So, oh, I almost made a mistake. I don't want to box that. That's not my answer. So again, I'll just go back to the triangle and label out which pieces we have figured out. So that is to say that the measurement of angle BAC, B to A to C, this is 31.42 degrees. And so it's simple arithmetic from the end. We know that from the third angle theorem that all of these need to add up to 180. So it'll be 180 minus the quantity of 100 plus 31.42, which is 48.58. So that means that our answer here, the measurement of angle BCA, this has to be equal to 48.58 degrees. And that is the answer to our warm-up question. Is this okay?
Yeah.
Yeah.
Okay. So I would now also like to ask, is there anything else we can know about here?
Can't we solve for all the angles?
So that's an interesting question. Can you? And this is probably one of the most mathematically rigorous questions I have asked all year because of how not obvious this is. Could you actually complete the rest of these angles? Is there enough information? So
Yeah.
let's go ahead and first figure out, like, kind of based on principle, whether or not it's possible, and then we can prove whether or not it is possible. I would go ahead and argue that we have 4 missing parameters, right? I would need to know this angle, this side, and we would have a complete description of this whole scenario, right? Is that okay?
Yeah.
Okay. If you had all that, you could even do additional trig and draw a line straight from the center to any edge to find a new triangle that you would have enough pieces to figure out. And then that would even let you define the radius, and you could know literally everything about this whole geometric setup. So that is to say that we would need to have control of some angle W, some angle X, some side length Y, and some side length Z. And I'm going to go ahead and argue right off the bat, this is actually impossible to solve. We can't learn anything additional about this bottom triangle Y. When we do trig, how many numbers do I have to give you for you to do a problem?
We need at least 3, and we only have 2.
You need at least 3 of the numbers of a triangle to do any sort of trig. Even when you use regular old SOHCAHTOA, technically you're only using 2 side lengths, but you know that you can use SOHCAHTOA because one of your angles is 90 degrees. That's what's providing that 3rd piece of information. So since there's 4 missing pieces of data here, nothing can be done. Now, we could suppose and be like, well, maybe there is some outside way that I could get the angles. Maybe I can use some trickery of the circle in order to more clearly define W and X. So let's go ahead and consider what information we could use to theoretically solve for W and X. I could say that W plus X plus 80 is equal to 180 degrees. Y'all see how I got that? That's just the triangle angle sum theorem.
Yep.
So that is to say W plus X is equal to 100 degrees. And since this equation has 2 variables, I would need 1 more equation in order to solve it. So to write 1 more equation that attempts to capture this, over here, right, I can make a smart statement about this, can't I?
So you could do 31.42 plus W equals 48.58 plus X.
They're not equal. Why would they be equal?
Oh, you could say...
That's not the rule for an inscribed quadrilateral. What's the rule for opposite angles in an inscribed quadrilateral?
They add up to 180, so you could say that they...
We could say that they add up to 180. That's the second equation I can write. So I can say that W plus 31.42 plus 48.58 plus X. So this is just saying the opposite angles of my quadrilateral, well, they sum to 180 degrees. Here's the rub. This is actually telling us that W plus X plus 80 is also equal to 180, which means that this information is exactly the same as the old information. And because these 2 equations are the same, there is not sufficient information here to solve for W or X, which means there is not sufficient information to solve for anything else. So the answer is nothing else can be known. However, how could this problem be fixed? What other number could I give you that would allow us to define this?
Radius?
That would do it. The radius would technically be enough information to define out everything else about this system, or just one of these side lengths. If I told you how long Z was, then that would be enough for you to go around and complete everything. But technically, there is 1 digit missing to define this lower triangle. That's just fancy stuff. I just wanted y'all to think about some higher end math stuff before the end of the year. Are there any other questions here?
No.
Okay. Let us quickly blast through that quiz. So on the quiz, like I said, I just posted the key so you could take a look there of the answers and the point values. All of the questions are worth 2 points with the following exceptions, just because I thought they were spicier questions. The following questions are worth double. Question 6, question 8, and question 9 are each worth 4 points, just because they are, I think, more engaging questions. They required combinations of multiple skills. If there are any questions about the questions, I'd be glad to do those now for you. in case you had any. Would anybody like to see any of these questions solved? Take a moment to look at the key that I put up so you can look at the answers. And if it's not clear how we're arriving at them, holler at me. And of course, if you would like a personalized grade breakdown, if you want to know which questions you lost points on, just shoot me an email and I'm always glad to respond to those when I get them.
Yeah, Mr. Robinson, I sent you an email asking.
I already responded.
Oh, did you? Haven't you?
Yup. I try to get those back as soon as I get them. Because I have like my little grading sheet in front of me, and I usually leave it out of the filing folder for a few days so that I can use it to respond to those emails. But after like Friday or whatever, I'll put it away, and I just like having stuff neatly filed away in my office because of how much stuff I have going on in here, man. It's like actually kind of difficult to keep it tidy. I like got my desktop and my laptop and all my school stuff and all my work stuff and all my video game streaming stuff from my Twitch channel. That's neither here nor there. Are there any questions on that stuff? And I think the spiciest one, question 6, I included the full setup there for how that one is solvable in case you want to know how 6 is equal to 29/4, Pythagorean theorem. Let me talk about the bonus. Oh, sorry, was there a question? I saw a little pop up.
No.
No good? Okay.
Yeah.
Let me show y'all the deal with that bonus question. So the answers to it, part A, if you take your calculator and you have it process regular old 0.79, I'm sorry, pi over 4. Pi over 4 is just 0.79. And then if you do the second part of that question, like I asked you to do, where you actually use that series in order to get closer to pi, the correct answer to part B is 0.76. But those of you who took a crack at it, what did you notice happening to the number every time you added one more term?
It was getting closer and closer to the original one, like the one that we did with the equation in the beginning.
But what did you notice about each step? Let me show y'all what I wanted y'all to take away from that second bonus question. So this is actually the Leibniz equation, Leibniz. And he's a name who you will see a lot more in math, especially those of you who study mathematics or science itself. You will see the name Leibniz appear everywhere because of how influential that guy was. He had the benefit of being alive at the same time as Newton and getting to challenge him to battle, which is a great way to build out a big resume full of achievements when you're trying to race Isaac Newton to all the important discoveries, right? But the Leibniz equation, that equation right there, adding up those digits, is literally how we process pi today. It's the best series representation we have of it. So this is to say that adding up all those fractions gives you exactly what 1/4 of pi is. The only problem is that to define it, you need to add up an infinite number of numbers in order to get the correct answer, which is to say that the actual number of numbers that we use just depends on how precise we need to be. So if it's your calculator, it's probably only adding up the first 100 digits. But if you were doing something real, like running a NASA database, you're using millions, if not hundreds of millions, if not billions of digits of pi, just to make sure that your calculations are as precise as they can be. And when you do this, you try to converge on pi over 4. That is 0.79, right? Because if we're just rounding to 2 decimals, we get 0.79 out of here. And what this tells us is that we can get there by doing the following. 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1/11 plus 1/13 minus 1/15. And the reason why I asked y'all to figure out pi over 4 before you began this exercise of actually adding up all of these digits was to see what these decimals do as you go along and add them up. What do you notice about these?
So they will get closer and closer to 1/4 pi.
That is vague. I'm asking specifically as we take a single step, what is happening? 0.8 to 0.7 to 0.8 to 0.7.
It's getting greater and then less,
Yeah.
and then greater and then less, and then greater and then less.
One overshoots it, one undershoots it. One overshoots it, one undershoots it. One overshoots it, back, forth, back, forth, back, forth, back, forth. This is how it can be that we can add up an infinite number of numbers. But no matter what, as we move forward, we get closer and closer to it. And this graph right here is a really good picture of it. So that blue line is exactly what pi should be. But if you take the series and you add it up as you increase the number of numbers that you add up, so this is the 50th number, for example, I just asked y'all to do the first 10. And in that first 10, it overshoots it, undershoots it, overshoots it, undershoots it, overshoots it, undershoots it. And the further and further we go out, the closer that we get to this number. But you can never actually have pi.
It's not definitive.
Let that soak. No, it is definitive. This is the sequence that produces pi, and yet you can never actually land on this blue line. All you can do is overshoot it, undershoot it, overshoot it, undershoot it. And as we move to the right, we get closer to the correct answer. There's actually a name for this. It's called using the squeeze theorem, because we're squeezing the two boundaries of this in on that blue line in order to capture it. But you can never actually have the blue line. Despite that fact, this is a complete description of pi nonetheless. Math is a strange place once you actually learn math. Is that okay?
Yeah.
Okay, great. Like I said, if you have any questions about your quiz scores individualized, give me a holler. Today we'll be talking about something a little bit more straightforward than what we've been doing, though where this information can become spicy is when it is asked to be combined with previous sections. Today we're talking about section 10.5, tangents of circles. And though the context in which I'm going to be talking about the word tangent today is with respect to circles, not triangles, this tangent is still loosely related to the trigonometric tangent that we have been talking about. So this tangent is related to our trigonometric tangent. But not identical. Depending on the context in which you are using a word, depending on the context in which you are using a word in mathematics, the word itself can have a couple different meanings based on the context. And so when it came to trig, what does tangent mean? Our most base definition of it.
Opposite over adjacent.
Yeah, so for some right triangle, if I have some angle theta, and from this angle theta, we have an opposite side and an adjacent side, and I won't even label that third one because I don't need to. We are aware that there is some tangent theta, which is equal to the opposite side length then divided by the adjacent side length. More generally in mathematics, a tangent has the following definition, and no worries, I will write out what I'm about to say in words down below, because this is a good definition of tangent. Though the only bummer is you probably won't see this definition of the word tangent again until you guys are seniors in 3 years in calculus. Or heck, who knows what the future holds? Maybe you get to calculus quicker. If I have some function here, and I could easily make a function that behaved this way, this is probably some kind of x cubed. A tangent is a line which touches this graph at one point and one point only. So this blue line, or sorry, purple line that I drew in right here is a tangent line, so long as it grazes this function at one point and one point only. So a tangent line, tangent lines touch other objects at precisely 1 point. And in fact, this notion of a tangent line is actually one of the central tenets of calculus. You will spend literally 2 or 3 chapters discussing the ideas and properties of this one idea right here. And here is the way in which these two things are united, right? You're like, what could these two things possibly have to do with each other? What does a ratio within a triangle have to do with a tangent line? Side note before we move along here, and I guess this is ironic because I'm about to do a tangent about a tangent. From English, have you guys ever heard the phrase going off on a tangent?
Yes.
Yeah.
Yeah, and so you have teachers like me and Flores who do it all the time. What does it mean for one of us to go off on a tangent?
Start talking about something else for a long
Yeah,
time.
yeah, you have a through line and then it reminds you of another idea and you go off on that other idea. This definition of the tangent is where that idea comes from in English. I'm talking about math, talking about math, talking about math, but instead of following the path that I should have gone, because the idea that I had touched this other idea at one point, I decided to go off on that idea instead. This is the same context as tangents in English. I had my main idea. And then suddenly I went off on a tangent about tangents while talking about tangents. Deal with it. Nonetheless, here is the main idea that we'll actually be using in here that unites these two definitions of the tangent. When we have a tangent to a circle, it's going to have some interesting properties, but let's go ahead and start off first just with the base definition. Oh no, my compass, hold on, the circle is ugly. The circle cannot be ugly, I do not permit that. Circle, center, gonna erase the ugly bits. And then I'm also going to add a single radius to my circle. So a tangent to a circle is a line which touches the circle at exactly 1 point. Tangent to a circle is a line which touches the circle at exactly 1 point and 1 point only. So the point where I want to have this tangent, well, that's right here. I want to put the tangent on that radius. And you'll notice here that when I try and draw my tangent line, if I make it too steep, is this a tangent?
Nope.
No.
It touches 2 points.
And if I make it too steep this way, is this a tangent?
No.
No. So you'll notice that if I tilt this line too much, it will end up touching the circle at 2 points. But if I try and make it just right, then I can make it so that it grazes the outside of the circle at precisely 1 point and 1 point only. Now, to prove what I just said, that tilting this line causes it to then touch at 2 points, if you were to take that idea, what I just said, and turn it into some equations that we could treat mathematically, you could prove what I'm about to say. However, you guys sadly don't have the math ability to do that because proving this next thing that I'm about to conject at you definitely requires calculus. It gets into this idea in calculus called differential geometry, where we literally do geometry using calculus. However, what do you think I'm about to say?
Slope or something?
It might be something about the slope. It might be something about how we could calculate the slope here. And then this would have to have the reciprocal slope.
Does it have to be perpendicular?
That is the rule. That you can show that if you constrain these requirements such that this line touches the circle at exactly 1 point and 1 point only, at the point where it contacts, this has to be 90 degrees to the radius. So that is to say that the one interesting property that tangents have is that at the point of contact, tangent lines are perpendicular to any given radius. Here is the way in which this definition of a tangent unites these other two definitions of tangents. Well, number one, I think it's pretty clear how it relates to this definition right here, right? It's touching the outside at one point and one point only. And when it comes to curves, we can define little circles in here with radii of curvature that let us define better that point, and they can give us the orientation of this tangent. I think that is pretty straightforward. However, what gets spicier is, what does this circle have to do with the trigonometry tangent? Well, let me show y'all a really wild and wacky picture. I'm sorry, not a picture, an animation, a GIF, if you will. Oh, heck, I just had it open in a tab. Wait, I'm so sorry, kids. I have like a million tabs open. Oh, here we go. Burn this into your brain. Go ahead and stare at this for a full 60 seconds. Look at what's going on in the bottom right. And then look at how that translates into what's going on above and below. And be sure to look at the names here on these graphs above and below. What do you notice here? So what's going on in the bottom right?
The angle is fluctuating.
The angle is slowly counting up as we count our way around the circle. And this blue line is reading off the width. So that's the same as reading off the x component of the edge of the circle as we go around. What do these x values become if we graph the x values alone? What is that blue graph?
It's the cosine.
That is the cosine. That's not even a question of math. You don't know that yet. That's just the way it's labeled. But as we also go around the circle, we read the up and down value, which is the same as reading its y component. And if you graph all of those y components together, what does that become?
Sine.
That becomes sine. So this is to say that the thing that your calculator is doing behind the scenes when it takes a sine or a cosine has something to do with the properties of a circle. That is to say that as you go around the edges of this circle, the x values become cosines, the y values become sines. Here's how this unites our two definitions of the word tangent. Every single point along a circle is an ordered pair that would give us back cosine theta, comma, sine theta. Cosine and sine can also give us tangent. If you take sine theta and divide it by cosine theta, according to SOHCAHTOA, what ratio is sine?
Opposite over hypotenuse.
Sine is opposite over hypotenuse. Cosine is adjacent divided by hypotenuse. And based on the way that fractions work, what cancels here in this ratio of sine divided by cosine?
Hypotenuse.
The hypotenuse.
And so sine divided by cosine is equal to opposite divided by adjacent. But what
Which
is
is
opposite
tangent.
divided by adjacent?
Tangent.
But that is also tangent. This is to say that you can get tangent of an angle by dividing the sine piece by the cosine piece. This is to say that as you go around the circle, you can relate the trigonometry of the circle itself to the properties of this tangent line. So again, this tangent would have a slope m, and this is actually equal to tangent theta, and that can be shown because this has to be equal to the y component of the circle, the sine, divided by the x component of the circle, the cosine, y over x, at any given point. Of course, this is way outside the scope of this class. I just want to make sure that y'all have some flavor for this, simply because this is not useful to you now. It's not operationalizable. But this idea that circles and trigs are related, you will see that again in pre-calculus. I just want you guys to be able to fill in that blank when it comes up. And also, This is related to a skill that you'll be doing in calculus once you guys learn how to calculate tangent lines to equations. Let's go ahead and go over now, since this is, basic geometry. Here's what you need to know about manipulating the properties of tangents to circles. Well, case one. Whenever we have something which is 90 degrees, that basically is a big red flag that you can suddenly do trig. That is to say that property one that interests us about tangents to circles is that if I know that something is tangent to a circle, if I know indeed that this outer line is tangent, and then we complete a triangle that involves a radius. Let me toss 3 points on here, A, B, C. Special property one, if BC is truly a tangent line, then we can make the conclusion that triangle ABC is a right triangle. And what can we do with right triangles?
Basic trigonometry.
Then you can use trig. Yep. That's basic property number one. If we know that BC is a tangent, I know that that is a 90-degree angle, and then the door has been opened to us to use as much trig as we have to in order to solve for missing properties. One question I like is I give you the hypotenuse and I give you BC, and then I ask you what the circumference of the circle is. Think about it. We'll probably do that for the warm-up tomorrow. Item number two, and this is where the properties get more interesting. This is the one that I will dedicate an example to today, just because we're getting to like the last 10 minutes of class. Though luckily this is the last important property. Please consider the following about the intersection of two tangents. And this one will require a bit of a fuzzy proof in order to justify, but I think once I give you the bits and pieces, it's pretty clear to see what I'm getting at. Okay, there's my circle, there's my center. And then I'm going to draw a radius. I'm going to draw another radius. I'm going to connect these two. Oh, you know what? Yeah, I'm going to draw two radii for right now, and I'm going to mark them as being congruent. That's how we know they're radii. And then I'm also going to add a tangent to each one of these. Tangent, tangent. So if two tangents of a circle intersect, then we can make the following strong statement. What does it seem, what does it look like is true? What's most likely true here? What appears to be the case?
That's a square, kind of.
No.
Quadrilateral.
Sure, that's boring. It is a four-sided figure, yeah. I'm looking for a strong math statement.
Altitude?
Nope.
Are the
Take one more
opposite
guess.
lengths parallel?
Opposite lengths parallel? No, definitely not. I could squeeze these two together or spread them apart, and that would definitely change the tilt and orientation of this, depending on how wide or narrow it was. More fundamental. Two of these lengths are congruent. Guess which?
The
The
radius.
radii.
Obviously, that's given.
Then the tangents are congruent.
The tangents are also congruent. If two tangents of a circle intersect, then their lengths are congruent. From the circle, or I should say from the point of contact, to their intersection. And I think that seems to be intuitively true here. And all I'm saying here is just for the sake of like mathematical precision, the length I am talking about goes from the point of contact to the point of intersection, from the point of contact to the point of intersection. So these are the lengths in question, here to here. And what that other brace is ugly. Don't draw braces like that. Gotta fix it, or at least try. I'll take it. Nonetheless, what I'm saying is that like necessarily, then these two things here also have to be equal. And here's my fuzzy proof of this. You could do a more explicit proof should you feel the need to, but I think this will get the idea across. In order to prove this idea beyond a shadow of a doubt, let me go ahead and add a real quick chord. And that chord goes from point of contact to point of contact. Now, here is what this chord allows me to say about this scenario that proves for sure these outside two side lengths are congruent. Well, number one, what kind of triangle is this? A radius, and a chord. We have a special name for this triangle.
Isosceles.
It has to be isosceles because two of the side lengths are congruent. And so I'm going to go ahead and call this A, B, C, D, where D is that point over there. So because A, B is congruent to AC, then we can say that triangle ABC is isosceles, right? And that tells me that this angle and this angle both have to be congruent. I'm going to go ahead and call each one of those X. I'm going to call that X as well, that this is X degrees, this is X degrees, right? And we have the second rule that if both of these are tangents, what's true there? What is this angle? This is tangent, this is a radius. What angle does a tangent make with a radius?
90.
This is necessarily 90 degrees. This is also necessarily 90 degrees. So on the opposite side here, if all of this adds up to 90 and this is X, what does the angle inside of this outside triangle have to be?
45.
That would be true if X was 45. You don't
Or
know
90
X is.
minus X.
You know that this outside angle here, right? If this is X and this is 90 in total, then this outside angle is 90 minus X. This outside angle here is also 90 minus X. So based on the fact that both of these base angles are necessarily congruent, so base angles of triangle BCD are congruent, that means that that outside triangle is also isosceles. So just a quick recap of what we've done. These radii are congruent. That means these angles are congruent. These angles sum to 90, which means this base angle right here on its own is 90 minus X. This one right here on its own is also 90 minus X. That means that this outside triangle is also isosceles, and because it is isosceles, therefore, triangle BCD is isosceles. Therefore, those outside lengths, BD, are congruent to CD. This is interesting feature number 2. If you have two tangents outside of a circle, if they are congruent, then the lengths on the outside of that triangle are also necessarily congruent.
Wait, Mr. Robinson, is angle A90?
No, this is agnostic to that.
Okay.
This is true no matter what. You could open this up as wide as you want. You could shut it down as narrow as you want. This proof holds. If that wasn't true, I would have given a number, but I didn't so that it would be true generally. And so what this leads to is that before we had the word inscribed, which means a shape is trapped inside of a circle. However, we can now have the opposite of that. we can have circumscribed figures. Circumscribed figures are ones which contain a circle within them. It is the opposite of inscribed. And that takes me to my last item for today. The following figure circumscribes a circle. Please solve for its perimeter. Okay. Oh, I'm sorry. Can't see the whole thing. So the following figure circumscribes a circle. Please solve for the perimeter of this quadrilateral. And so, the thing that makes it a circumscription is the fact that it contains the circle completely within it. And oddly enough, there's actually enough information here to solve for this circle, or sorry, for this quadrilateral's entire perimeter. I'm going to start off with the given information here just being in black, and for all of the additional data that we solve for as being purple. How can we use the information that we just learned?
That when the tangents intersect, like those, they're congruent, the lengths that, I can't explain it.
When two tangents intersect on the outside of a circle, their lengths from the point of contact to the point of intersection, they're congruent. So whenever you see a circumscription, please go around and make the following marks. Yo, this length and this length, they have to be congruent. This length and this length, they have to be congruent. This length and this length, they have to be congruent. This length and this length, they have to be congruent. And so that allows us to go around and figure out what all of the missing lengths are, every single one of them. If this is 4, what is this?
4.
Okay, we're getting there. If this is 3, what is this?
3.
So we got that. What about this? How can I learn that?
You could do 6 minus 14.
Say that again.
You could do 14 minus 6.
Good, this is 6, and these two are congruent, so therefore this junk here, that's got to be 6. And then subtraction tells us that this missing piece is what?
8.
This missing chunk there, that's got to be 8. So therefore, big brain moment, this last piece that we would need in order to get the perimeter, that's also 8. So now all we have to do to get the answer is go around and add them up. So this is going to be 7 plus 10 plus 14 plus 11. So what, that's 21 plus 21? 42?
Yeah, it's 42.
Yeah.
Great. Okay. So, quick overview of what we talked about today. Up front, the word tangent has a lot of uses in math, and even though it seems different in different contexts, they are all related in a really interesting, complicated way that you won't really get the full picture of until you are done with pre-cal. That will give you your first glimpse into tangents in a brighter light. And then finally, calculus gives you the final big story about what tangents are all about. In this context, all that we really need to know is that tangents touch a circle at one point on the outside, and that has some important implications. Implication 1, For that to be true, it needs to make a 90-degree angle with the radius, and whenever you have something that makes a 90-degree angle, that's typically a hint that we're talking about trig. So if you have a triangle, which is formed by a radius, a tangent, and some third length to be a connecting hypotenuse, red flag, we're doing trig. Item number 2, because of some fancy properties of isosceles triangles, if two tangents intersect on the outside of a circle, then from the point of intersection, from the point of contact to the point of intersection, from the point of contact to the point of intersection, those lengths on the outside of a triangle also form an isosceles triangle and therefore must be congruent. This is useful because it allows us to solve these types of circumscription questions. If you trap a circle within another shape and it touches on all sides, we can say that these lengths are congruent, which allows us to solve puzzle questions like this. Last thing that I'll say, and I guess today class is ending right on time, the SAT doesn't matter anymore, but this used to be a topic on the SAT. So if that's a thing you're prepping for, just know that this comes up. You'll see circumscription questions, but I don't think any of you will be needing to take it because I think the UC might have killed the SAT. But that is neither here nor there.
Well, is it only the UC?
For now, but they set the standards for all of the other colleges that matter. If they do a thing, everybody else does it. I would consider the following. You go to a high school in Pasadena that has nothing to do with the official UC system, and yet your entire class schedule is A through G approved. Do you guys know what A through G approval means?
No.
A through G approval means that our high school curriculum is good enough, it is rigorous enough for you to apply to a UC. The UCs are so influential that they set our curriculum even though we're not affiliated with them in any official way. It's just so that you can be eligible to apply to that system when you become high school seniors. That is how influential they are. If they do a thing, other people will follow. Also, second thing that is neither here nor there, in about 1 hour, depending on the weather, today will be the first time a private company sends human beings into space. SpaceX is having a test launch today at 1:30, which is historic and important in terms of the space flight industry. And if you are interested in space flight or aerospace engineering or anything of that nature, I would follow that, because if this goes well, it'll be the beginning of a new era. If this goes poorly, that'll suck. The weather wasn't looking super great, so they might end up canceling it or postponing it. But so long as the weather allows them to conduct a launch today, Elon Musk's SpaceX is going to be sending 2 astronauts to the International Space Station.
Oh wait, when is it? Is it possible to see it live somewhere?
Yeah, I think it's just NASA.live, or if you just Google SpaceX right now, I guarantee you it'll be the top hit on every news item. Launch is scheduled to take place at 4:30 p.m. Eastern, which is 1:30 p.m. Pacific. So it should be in about 1 hour, about the end of lunch. Anyway, thanks for listening. You all have a really nice day. This video will be going up on YouTube momentarily, along with your homework. Tomorrow we'll have workshop time so that we can work on it together and you can check your answers. But in the meantime, you have a very, very nice 23 hours.
Bye, Mr. Robinson.
Thank you. Bye.
Bye. And oh yeah, and see you next
Bye.
week on Friday. Bye, everybody.
Bye.
Peace.